Hello, Math 1. This lesson is on 10.11, which is your introduction to scatter plots. Now, everything you guys have dealt with so far up to this point has been, data that's aligned perfectly in a straight line or, as an exponential graph or a perfect exponential decay graph, right? So now we're going to take a bunch of points and create a scatter plot that shows a relationship, right, that we can fit a model to. So a scatter plot basically has points that show the relationship between two sets of data, right? And when we look at that, the two sets of data, we'd be looking at like an X and a Y. Now what happens is if you plot a bunch of points, you'll see that they tend to have a pattern, right? They don't line up perfectly, but they line up closely in a certain pattern. For example, this first one, what this here is, this scatter plot is a scatter plot of what we call a positive correlation. And the reason is we could draw a line through this set of data. And when we look at this line through the set of data, we know that we can fit a line with a positive slope through it. Now, if you look, each of these points are very close to the line. They're not on the line, but they're close. So we can say that kind of fits a linear pattern. So the next one, we would say has a negative correlation. And the reason we say it's a negative correlation is we can draw a line through that set of data that gets close to every point, right? And that line has a negative slope. Now, when you look at the third one, these points are all over the place. They really show no relationship. So what we say is this has no correlation. Now, as we get down here, when I look at these dots, right, yeah, you could draw a line through it, but what we're going to see is we're also going to have a correlation that shows exponential growth. But then we'll also have one that tends to mock exponential decay. All right. So these are the 5 correlations we're really going to talk about. Positive correlation, negative correlation, no correlation, exponential growth, or exponential decay. Now, a correlation coefficient, right, is what we, it's denoted by some R value. And it is a number from -1 to 1 that measures how well a line fits a set of points. Okay, so the closer the line is to all of the points, right, the better the correlation coefficient. If your correlation coefficient is close to -1, right, that means it's a very strong linear relationship and that line has a negative slope. If it's close to 0, there is no relationship here. No relationship or correlation. If it's closer to 1, that tells you that it's a very strong linear correlation and that the line would have a positive slope. Okay, and we're going to talk about this a little bit as we move along. So remember, the closer to -1 or 1, the stronger the linear relationship. Next, let's take a look at this. So remember, it says determine if the data displays a positive, negative, or no linear correlation. Determine whether the correlation coefficient for the data is closest to -1, -0.5, 0, 0.5, or 1. So when I look at the first example, these dots kind of show a pattern. I can draw a line through that data, but it's the dots or the points are not really close to the line. But it does show somewhat of a pattern. So we would say that this has a negative correlation. And the reason it's negative is because the slope of that line is negative. Now, it's not a really strong correlation, so we're going to say it's not 0, it's not -1, so we're going to say it's about -0.5. Right? Letter B, if I look here, those points are all over the place. No line can be drawn to get close to all of them. So we would say this is no correlation. Now C, on the other hand, if I draw a line, this line gets really close to all the points. So those points all line up in a very close linear fashion. So we would say this is a positive correlation because the slope of that line would be positive. Then we would say all those points are very close to the line. So we would actually say that has a correlation coefficient of 1. Now the next one, you can see it kind of has a positive slope to it. It's not a very strong relationship because the points are far. So we'll actually give this a positive correlation. Since it's not very strong, we're going to say it's probably about -0.5. Letter E, if I draw a line through here, that line gets close to all the points. So we say that would be a negative correlation. And all those points are really close to it. So we would say that it's probably a correlation coefficient closer to -1. And if I look at F, there's no line that can come close to all the points. There's really no, positive correlation or negative correlation. So here we would say there's no correlation. So what we get into is what we call regression analysis, right? So what we're going to do is we're going to take a set of statistical processes for estimating the relationship between a dependent variable and one or more independent variables. So what we're going to do is we're going to take this data set, right? And we're going to try and fit a line that comes close to every single point in the set of data, right? Now, there's two models that we are aware of already. One is a linear regression. If your ordered pairs or your points line up in a very close linear fashion, meaning a line can come close to all the points, positive or negative slopes, right? That means that would be a linear regression model we would use. If your points tend to mock, right? If I take these ordered pairs and they don't make a straight line, but they show exponential growth, or they come close to exponential decay, we would use an exponential regression. Okay. Now, we can actually run both regression models on sets of data, and we can actually use what we call the coefficient of determination, which is the R-squared value. And this is a statistical measure in a regression model that determines the proportion of variance in a dependent variable that can be explained by the independent variable. It basically, what's important for you to know, it shows how well the data fit the regression model. Now, this R-squared value will always be between 0 and 1, right? And basically, we say the closer to 1, the stronger the correlation. Okay? So keep that in mind. We want to be as close to 1 as possible. So what we're going to do is we're going to use Desmos and Google Sheets, right, to create this regression model. All right? So what I want you to do is open Google Sheets and Desmos real quick. So right now I have Google Sheets opened, right? And what I'm going to do, it says here, the table shows the number Y in thousands of alternative fueled vehicles in the United States X years after 1990. approximate the best fitting line for the data. So you have to understand is like when x is 0, that tells you that's 1990. X is 1, that's 1991. So what we're going to do is we're going to make two columns here. We're going to make a column for x and a column for y. So we're going to take our x values and we're just going to type them in, right? So 0, 1, 2, 3, 4, 5, 6, and 7. Okay, then we're going to take our y values and we're going to plug them in. So remember, this table on the paper is horizontal, but we can transfer it to be vertical. Doesn't matter. So you got 280, 295, 322, 395, 425, 471, 511, and 548. Okay, so if you look here, we have all of our data here. 0 to 80, 1 to 95. So what we're going to do is we're going to highlight all of these cells. Okay, and when we highlight all of these cells, I'm going to right click and I'm going to copy. I'm going to copy that data. Now what I'm going to do is I'm going to go to Desmos.com and I'm going to go to the graphing calculator. And in this box here, I'm going to basically hit Control V to paste that in there. And if you look, what comes up is the set of data, all the points in the set of data. Okay, once I have that data in there, what I'm basically going to do is start another box down here. So if I click down here, I can start another box. Now, the first thing we want to do is we want to determine, does this data tend to form a line? Does it come close or model a line or an exponential growth or decay function? When I look at it, it looks like it's going to be a line. So we typed it in, we highlighted data, went to Desmos, typed it in, and this is our data. So what you're going to do now is you're going to type this in. Since we determined that it models a line, we're going to type in, you're just going to hit Y and then just type in 1, and it automatically does that for you. Now you're going to use the tilde sign, which is the shift, and the button to the left, you'll get the tilde, right? So it's to the left of the number 1. So you have to hold shift down and the tilde. And then all you're going to do is type in mx1 plus b. And right there, what they tell you, that number 1, they give you this line. If you look, that line comes very close to every single point. That line is the line that fits the data the best. And they actually give you the equation here. They tell you the value of m, and they tell you the value of b. Okay, and the best part is if you look at the r value, right? R is close to 1, right? And it's close to positive 1. Therefore, you know it's a pretty strong correlation. And the r squared value is really close to 1. So we know that it is a pretty good model to fit this data. So we would go to our paper and we would write this model down. And that equation, so you would take the value of m and the value of b and plug it into y equals mx plus b, and that's the equation that best fits your data. Okay, so we're going to do a couple here, right? So I want you guys to, we'll do one or two together, and then I will put the answers for the rest of them down. So for the first example again, right, all we're going to do is type in our x values. So we got 9 and, let me make sure I'm in here. So I go to Google Sheets again. I'm going to go 9, enter, 9.5, 10, 10.5, 11, 11.5. Okay, then I'm going to delete these. And then I'm going to come up here and I'm going to go for my Y values. 69, 70.5, 71.5, 72, 74, 74. Right? So once I look at this again, I highlight the data. I right click, which is 2 fingers, I believe, for you guys, right? For right click, you're going to copy. Then you're going to go to Desmos. Right away, you're going to, if I click X there and X there, I can start over. I'm going to go ahead, Control V. There's my table. If I look at my data here, right, it tends to show a strong linear correlation. So I'm going to come down here, since it looks linear, Y1 tilde mx plus b. Oh, mx1. Sorry, mx1. You have to make sure you have the 1 there. If I look, the R values, it's still relatively close to 1. R squared is a little less than the previous one, but it's still a very good model for it. This comes close to every single point. There's my slope of the line. There's my y-intercept. So now all I'm going to do is take those values, right? So we're going to say this tends to be linear. The regression model, I'm going to take is y equals 2.05x. And let me go back to 2.05714x plus 50.7 plus 50.7. The R squared value was 0.95. So if I look, I'm going to get the R squared value from right here. It's 0.9576. And we are done. Okay, so let's take a look at another one. So I went ahead already and I copied the data in there, right? So we're working on example 3, and if you see, I put the data in there. I'm going to go over here. I'm going to copy. I'm going to paste it into Desmos. Control V. Once I do that, I look at my data. There's really no correlation here, right? So when I look, I can try and fit a data to it, right? I'm going to say if anything, this would be more exponential. If I wanted to do exponential. Remember, if we wanted to do linear, right, we could do y1 is approximately basically mx1 plus b. Or if it's exponential, we would use this one. Y1 is approximately a times b to the x. So here's the thing. What we'll do is we'll actually do both models, right? Although it doesn't have a strong correlation, here's what I want you to see. If I do y1 tilde, right, mx1 plus b, right? And then what I'm going to do is I'm going to actually create an exponential model too. So we would do y1 is approximately a times b 2, and remember it's caret key, to the x1. And if you look there, right, here's what's nice about this. Notice the R squared value. Neither of these models really fit this data well because the points are so spread out, there's really no pattern. But if you wanted to compare the R squared values, this one has an R squared value of 0.1368. This one is 0.1774. What this tells me is if I were to use a model, the exponential model is closer to 1, so I would actually use the exponential model. But really, neither of these are really good. So for this, I'm just going to say neither. Okay, now the next one. I'm going to go and type the data in, and then we'll take a look at it. So when I look at example 4 here, right, I type the data into Google Sheets. I'm going to come over to Desmos. Oops, I got to delete the previous one. And I'm going to paste the table in. If I look at this data, right, if I look at it, definitely tends to be linear, right? They almost line into a perfectly straight line. And look what happens here. Since that's linear, we know we're going to use y1 tilde mx1 plus b. Once I type that in, notice how that line goes through all the points. And if you look at the r squared value, it's 1. That's because it's an exact model for this data. The slope of this line is 4 and b is 6. Okay, so we're going to come over here. We know this is definitely going to be linear, right? The regression model is y equals, let me go back real quick. It was 4x plus 6. So m is 4, b is 6. So y equals 4x plus 6. And the r squared value was 1 because that's almost an identical fit. Okay, I'm going to go enter example 5. So for example 5, I'm going to again go ahead and copy. So I basically typed in all the data. I copied it, coming over to Desmos, paste it. Once I paste it, now I look at the data. So I'm going to zoom out here. If you look at this data tends to mock exponential growth. So we know the model we want to use is y is approximately a parentheses b to the x1. Oh, it's y1. I forgot the 1 with the y. And if I look at that there is an exponential function, and it actually hits and goes through every single point, which is why your r squared value is 1. So I know right away from this, I know this is exponential, and it would be growth. The regression model, they give me A and they give me B, right? So A is 1.1991 and then 2.8. So we would say y equals A, 1.1991 times, if I'm not mistaken, it was 2.8. And that would be to the x power. Okay, the r squared value here was 1 because it's an exact fit to that data. Okay, I want you guys to go and do 6 and 7, and then come back and check your answers. So when we look at example 6 real quick, notice the data tends to be exponential decay here, right? So what I did is I used the exponential regression model, and our r value became close to 1. We're at 0.9178. So the model would be 159.039. So here's the thing though, I want you to see, so y tilde mx1 plus b, y1, sorry. And if you look, the r squared value for the exponential model was 0.91. The r squared value for the regression, the linear regression was 0.83. So you can tell the better fit is the exponential decay model. So we would say this is exponential, and it would be decay. And your regression model would be y equals 158 times 0.93 to the x. So y equals 158 times 0.9, what was it again? 0.93 to the x power. Go ahead, try the homework, and let me know if you have any questions.